we'll take a small break from what do you call threshold graphs, so that you have enough time to absorb it, and we'll do first lossy kernel for cycle packing in the next few lectures, next couple of lectures, and then go back to the threshold graph when you have absorbed a little bit. But what I am going to do today is not even that. What I am going to do is today is going to prove a completely combinatorial lemma about certain kind of object. Okay, so what I am going to talk about today is what is called universal independent set covering. Okay, so what is an universal independent set covering? So we will use this finally to see what do you call lossy kernel for cycle packing and disjoint factor. But in this lecture, we don't have to worry about any definition from lossy kernel or something. We'll just concentrate on this combinatorial lemma which I would like to prove today. So first let me introduce the object of our interest. What is the object of our interest? Okay. Okay. So I'm going to define a notion of, let's call it universal independent U. Okay. In fact, what will be, we are going to call it universal U-Lisk, okay, or universal labeled independent set covering. Okay. Now, in short, I am going to write U-Lisk. Okay. So what is this? What does it take? It takes as an input a graph G, integer Q, and a labeling function or a coloring function, whatever you want to call it. Let's call it labeling function. Is this called gamma? What is this? Which is basically, I'm going to denote by Q, right? And there's a labeling function. What is this? Is it gamma, delta? What is this? Gamma? Gamma. Okay. Gamma from V to this. Okay. So this is our input. And what is our output? Output is going to be a subset X of Vg with the following property. So output consists of a subset X, subset of Vg, okay, such that for any independent set I, okay, for any independent set, okay, so a subset X subset of Vg such that for any independent set S in G, okay, S in G, there is an independent set okay, there is an independent set S prime in graph induced on X, okay, there is an independent set S prime in graph induced on X with, if I look at gamma of S prime, it is contained inside gamma of S. So I will come to that what it means, okay. So what is the gamma of S prime? You basically look at this set of vertices and collect all the labelings which it has got, okay. So it has been colored maybe by red, blue, green, yellow. So look at this red, blue, green, yellow, that is part of gamma of S prime, and the labels which gamma of S prime has got, look, gamma is a function. So what is the gamma of S prime? Labels assigned to vertices in S prime, okay. So this is a set of labels which have been assigned to vertices in S. So it is possible that there are many vertices in S which have been assigned the same color 1, but I am not interested in what, I am just collecting all the set of colors which S gets, and all I am saying that I have a subset X subset of Vg such that for any independent set S in G, there is an independent set S prime in graph induced on X such that the label set of S prime is contained inside label set of S, that is the first property. And what else? And the most important thing is that this is where cardinality of gamma S prime is not too small, is at least 1 minus epsilon time cardinality of gamma S. So first of all, right, okay, and the set X is called epsilon Ulesk. Yes, fine, okay. So what is this? We are given a graph G, we are given an integer Q and a labeling function from Vz to 1 to Q, and the objective is to output a set X such that you give me any independent set S in G, okay. I will give you an independent set S prime in graph induced on X with the following property, that the label set of my S prime is contained in the label set of S, and the more importantly is that, okay, it may not be that it contains all the labels which has been assigned to vertices in S, but it contains almost all the labels which has been assigned to this, and that is quantified by the factor the number of labels on S prime is at least 1 minus epsilon times the number of labels used on the set S, okay. Now that is our goal, okay. So this is why it is called universal labeled independent sets coupling, meaning in the sense that for every independent set, yes, yes, we will come back to that, sure, output it, right. So that is what we want, right. I mean, yes, our goal is to output as small this is possible, right. So we will come back to that, I mean, okay, fine. So first let us understand what is our goal, right, what do we expect from an output, right. Now I want to output a set X with a certain properties, right. It is really, I mean, why it is important, because you give me any independent set in my graph, I have a close approximate in terms of label set in my set X. Does anybody has any problem with the definition? Okay, fine. Okay, so now of course, as pointed out by Prateek, I mean, just output, yes, that satisfies all the properties. In fact, you do not need any epsilon there, it satisfies exactly, right. But the goal is that our objective is that can for some class of graphs, right, some class of graph we can output a set X which is much smaller than the size of the graph, right. Of course, objective is to minimize size of X, okay, fine. Okay. So I do not know how to construct this for different classes of graphs. So this is a combinatorial question for people who are interested in combinatorics, for which class of graph, for which kind of parameters one can obtain X with good size bounds, okay. But what I am going to tell you is that if G is an interval graph, then I can do something interesting, okay. If G is an interval graph, okay, then I can find an epsilon Eulisk of small size, whatever that means. Then I can find epsilon Eulisk of small size. That's my goal. Okay. So I hope everybody knows what interval graph is. Okay. Okay. So from now onwards, whenever I will say graph, it will always be implicitly interval graph. Okay. From now onwards, graph means interval graph. Okay. 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 So that is what I want to achieve today. Question? Comments? Rohani?
Has this anything to do with the multicolored independent set?
What is a multicolored independence?
You are given a labeling function that defines a partition of your graph into Q parts. And suppose you are interested in finding an independent set that picks, say, at most one from each color class.
So look, no, for two reasons. This, okay, why? Because this x which you are giving could be of any arbitrary size, right? And this labeling function may not be an independent set.
No, I mean, okay, forget that condition. I mean, I'm saying, forget the second condition. It's like, see, I'm saying without loss of generality, maybe you can assume that X is an independent set.
No.
So in the worst case, suppose there was an independent set S which contains all the colors 1 to Q.
Yes. If there was, then I will take that independent set. Yes, that's a great object.
Yeah, yeah, exactly. So
but I may not have.
Yes. So if you have such an independent set, it is like solving a multicolored this thing. And if you don't.
Multicolored what?
Independent set.
We are not solving any problem. We are not trying to solve any problem. Please try to understand. We are not trying to solve any problem. Look, all it tells us that for every set, independent set, I must have this property. Finding a object is very different than something which happens for you. Give me your favorite independent set in your graph, and I should be able to. So like you are like an adversary, and I am weak person. So you are trying to defeat me, right? So and I have computed this at x, whatever it is. Now you give me this, I have to give you a label function. Like I have to give you something which closely approximates this independent. Yes, you're completely right. If I can find an independent set, if, and look, we are not even talking about algorithm at all at this point of time, right? We are just talking about the existence of an object of small size. So forget about algorithm for that matter, right? Like, so there is no algorithmic question at this point of time, right? How will we compute and not compute is very intelligent. At this point of time, even just an existential question, right? That if I give you a graph G with any labeling function, right? I haven't told any labeling function, right? So given any graph G and any labeling function from blah to blah, right? Graph has been labeled. I want a set X of as small size as possible. For example, can I find an X question? Can I find X such that cardinality of X is less than or equal to function of like Q, for example, right? Not clear, right? Right? So it's like, yes, if I could find a multicolored independent set in my graph, yes, that's perfectly fine. That's my X.
For this thing.
Yeah, because that's a skew size object, right?
Yeah, no, I'm saying for this thing, can't you actually find a set X which has size some function?
I don't think so. I don't think this is correct that you can find any function of Q for any graph.
Because you give me a labeling function.
Yes.
And look at the partition of the graph for that labeling function.
Yes.
And now for any subset of Q.
Yes.
Look at the graph restricted to only those partitions.
Okay.
Color Q.
Okay.
That subset.
Okay.
Now in that I'm saying find a multicolored independent set, any multicolored independent set. So that will pick exactly one from each color class, if it exists.
Okay.
Find those sets. Now take a union of all the sets corresponding to every subset of Q that you have.
Okay.
So now I'm claiming that's my X. For that, I have to prove this property.
Okay.
Maybe it's stronger. Let's see. So now you give me an independent set. I'm just interested in looking at the colors. So look at which colors it belongs to.
Fine.
So restricted to those colors also it's independent. And
Yes.
now, for that subset, I've stored some X, right?
Okay. Okay. Very nice. So you can do it in 2 power q times q. Okay. Very nice. Give me poly q.
We don't have a multicolor independence of model. Still nothing. Because if you don't have a multicolor independence of restricted, so there'll be no subset that will be using exactly those colors. Those Q colors. And in fact, this is, of course, this is asking for some, I mean, we are, what we are actually giving is a spray with exactly the same colors. And this is a more relaxed thing that
And I don't think for any graph it exists. If I give you epsilon, I don't think it exists. What?
With this construction, can we ensure the second property?
It is satisfied with epsilon equal to 0.
we're actually giving the same color sets.
Suppose you give me, there was some independent set S which picked a whole bunch of color from one color class itself. And when I say color, when labeling itself.
No, true, but what you are interested in is just it's a cardinality of the color set and not the cardinality of the sets.
Okay. More questions?
When you say that it doesn't exist for any general graphs, what is it that
It does not exist as a poly size object, and I can give you a construction that it cannot exist. For any epsilon, like, but epsilon needs to be a fixed constant, right? I mean, if epsilon becomes a function of q, then there is nothing, right? Then I can take 1 over 2 power q and then I am perfectly fine. Okay. So what we are going to construct is something which is not going to be a function of q, but it is going to be a function of something much more fundamental. Okay. Okay. So what I am going to construct is an epsilon Eulisk for interval graphs of size roughly I mean, I really hate people coming to my lectures late. 11:30 is not, to all of you people, 11:30 is not 9:30 that you have difficulty waking up. So for interval graphs of size q times chromatic number of G times order 1 over epsilon log 1 over epsilon. So this is what I am going to construct today. So this is what I am going to construct. An epsilon Eulisk for interval graphs of size q times chromatic number to the power order of 1 over epsilon log 1 over epsilon. This is what I am going to construct. Okay. So if these two numbers are small and epsilon is a fixed constant, then this is a polynomial size. And this is what I am going to use it to design my kernelization algorithms. okay. So for my design of my kernelization algorithm, this object is of our interest. So more precisely, the theorem which I will prove to you, okay, fine. So this is what my goal is, to give you a construction, an epsilon u lisk for undirected graph, okay. What is the theorem? Okay. So essentially, I am going to prove the following lemma to you, or lemma or theorem. Okay. So the lemma is, let G be an interval graph let G be an interval graph Q in natural number epsilon greater than 0 and gamma is a labeling function from vertex set to 1 to Q, and then there is a polynomial time algorithm. That is important, because if I am going to use it for kernelization purpose, I should be able to construct this in polynomial time and of polynomial size. Then there is a polynomial time algorithm that constructs x epsilon u lisk of size q times qz log 1 over epsilon such that x is epsilon u lisk of g. Okay. So that's a theorem lemma which we are going to prove. Okay. So for now, okay, so let's make one assumption, and that wouldn't change much later. So what we'll assume for now, okay. So to prove this, we'll prove several set of lemmas and this, but for a ease of presentation, let's assume for now, okay. Let us assume that gamma from Vg to Q is a proper coloring. Okay, is a proper coloring. I am going to assume for now that it is proper coloring, and later I will replace how I can make, given a labeling, I will tell you how I can make it a proper coloring using these many colors, right. So has a proper coloring. So basically I should give you an algorithm with running time q power big O of 1 over epsilon log 1 over epsilon for now, and then I will tell you how I can get rid of, how I can make, given a labeling function gamma, how can I convert to another labeling function, say delta, right. From gamma I will convert it to delta, right, that q will go to q times chi of g such that delta is a proper coloring. Okay, delta is a proper coloring, fine, but we will do this transformation later. Let's just for now let's assume that this is, so that we understand the right things first, and then we we do the small objects later. Okay. So now what strategy should be applied? Okay. So okay, let's take forward what Rohani's strategy was. What she said, that fine, if I have a set S, right, if I had a multicolored independent set, whatever that means, okay, if there was a multicolored independent set, just take that and you are done. Okay. But the problem is I may not have a multicolored independent set, and then I need to do something else, right, to take care of everything else. Okay. to define everything in every term, to define everything, let me introduce couple of terminology which is not very hard, but it will kind of tell you what kind of objects, okay. Okay. So now let me define notion of realizability definition, okay. This is called realizability definition, okay. What is this? A subset Z subset of Q is called realizable, okay, is called realizable if, okay, let's assume, okay, realizable if, what do you think should be the definition? I want to say the subset is called realizable in G if, what should be the definition, right? What should be the definition? It's called realizable if, I mean that if there exists an independent set X in G such that what happens? If I look at the colored set of X, this is exactly equal to Z. So then I will call realizable. So this subset of labels is realizable if I can find an independent set, this. Look, and we can always say it is equal because you just, if you had some bigger set which realizes this X, right, realizes the labels Z, then just delete all those labels which are not present in Z, and then you will still got an independent set, right. So we can always say equal. So this is basically going from inverse. So basically what are we saying here? So now in this language what are we saying? For every independent set, right, I will be able to find something which is realizable. First of all, I will give you set such that the realizable set or the set of labels is very close to whatever we want. Okay, fine. So this is the notion of realization, okay, which we will use. Okay. Now the another definition, okay. So for want of, or for just to be synonymous with what is it called, with our okay, our notion, I am going to slightly change notation. I am going to use this as a delta, and here I am going to use K, okay, it does not matter. And what is K? K is nothing but, as I was trying to tell you, K, Q times chi z, okay, just to make our notations much more simpler and clear, and also when you read from the paper you find the same notations everywhere, okay. But we will come to this transformation later, okay. Now the struggle was to come up with the right definition of whatever she was saying, right, what she said is that fine, if it's okay if I do not find a multicolored independent set, what should I do, right? I mean, what is the right notion, what is the right definition which can replace that terminology and we are still able to happy, because what are we allowed to do? We are allowed to lose certain amount of labels, right? So you have some freedom. What is that freedom? The freedom is that, look, I do not demand that for every independent set you give me another independent set with the same label set. You can lose some, and that lose some is quantified by epsilon, right? Now I would like to utilize that, okay, and it took some year before we came up with the following definition, okay. So now I am going to delete this for now. I hope you have, I will delete this also after some point of time, but let us now try to understand what it means. Okay. So sometimes you need to have a right definition to do anything, okay. So the definition we said, let G be a, for now it is an interval graph because I have always told you that is an interval graph. let G be a graph okay, let G be a graph and delta be this, okay. A label will be called poor or rich based on how many times it appears on a vertices, okay. So a label L in K is called rich, okay. Rich in H, it's called rich in H, okay. Let H be a graph because it will be, let's define it slightly differently, because let H be an induced subgraph of G. Let me define it much more clearly because this is what we will need in algorithm. So let H be an induced subgraph of G and delta is this. A label L in H is called rich in H if at least K vertices in H is labeled what?
Is called rich or what is
If at least K vertices in H is labeled L, else the label is called poor. Yeah, so I am defining with respect to H, right? Because, right? So let H be an induced subgraph of G and delta is a function from labeling function from Vg to K. And I say a label L in K is called rich in H if the number of vertices which has been assigned this label is at least K, otherwise it is called poor, okay. Now, okay, fine, okay, so can you find a multicolored independent set which contains all rich? Okay, so right, so what, look, so what you said, let's go back. So you said if we can find multicolored independent set, and by multicolored independent set, an independent set that contains all the labels, and we can always assume that this independent set contains, the size of this independent set is exactly equal to the label set, because delete, if there are too many vertices of the same label, delete, it will not change independence. So I said that, look, now I said, can you find multicolored or rich independent set, okay. Let us call it rich independent set. What is rich independent set? It is a set which is independent and it contains all rich labels, all rich labels. So this is analog, right? I am saying that, okay, fine, I do not know how to find multicolored independent set, but can I find rich independent set, right? Multicolored rich independent, like a rich independent set, an independent set X subset of, let's S subset of Vg or X subset of Vg, such that if I look at this, okay, this is exactly equal to rich labels.
Richness is with respect to H. You want X to be in H or G is in
It doesn't matter. B of H. Okay. So now here's my question, right? So G is an interval graph. I give you an induced subgraph H of G, which is, what is the property? That it has certain set of rich labels, right? It has certain set of rich labels. What is rich label? If the number of blah blah is more than blah. Now my question to you is, then I am claiming to you that you can find this. It's an interval graph. Yes.
So whatever is said before.
What?
Oh, that 2-part Q.
It doesn't matter. That's okay. Forget it. Right? If I've been given a coloring, how does it matter? Like, Yes, it is hard, that is fine, I am just talking, but now I want a polynomial time algorithm because I also have an interval graph. Okay. So suppose we do have an algorithm to find a rich independent set, okay. So we will write down, let us write down this lemma, we will come back and prove all of them, let us not worry about not proving them, okay. So I am making lots of like bullet points. First, this is a which I need to prove to you, that how can we make such a transformation. Now I told you that I define a notion of rich and poor, and what is it, and now what is my lemma? My lemma is, let H be an induced subgraph of G, okay. Let H be an induced subgraph of G, delta be a labeling function, and R be the set of rich labels with respect to H, okay. Then first question, okay, I mean this is also not clear, then R is realizable in H, right. I mean we said yes, 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 all the things, but first of all then R is realizable in H. R is, look, it is just set of rich labels, right, but why first of all there is an independent set which realizes that is also not clear, right. Then R is first of all realizable in H, and what is the next property? Realize, moreover an independent set realizing R can be found in polynomial time. That is it, okay. So this is our main lemma, this is one of our main lemma, right. So suppose we had this, right. So what will be our strategy? So our strategy will be that, look, right, now what could be our potential strategy should be, right. Oh, it looks like we can pack rich labels, right. So if there are lots and lots of rich labels, right, most of the labels are rich, then you should be happy, right. So suppose number of rich labels is strictly greater than, suppose R in my G for example is strictly more than 1 minus epsilon times say k, number of rich labels is too large, right, whatever that, okay. Then what happens? Are we done? Then I apply this, it will output me some set X which realizes this. Are we done then?
Because for any independent set as gamma of S is at most k.
But look at any other independent set, okay, fine, okay, any independent set, right, of any independent set, but still what happens if, look what it says, but I could still have an independent set here, right, I do not know how to handle them, right, even if this is large, right, if this is whole thing then what she was saying was exactly the same thing, right, then you have, but suppose this is the divide of rich labels, okay, it does not matter, and this is a divide of poor labels, poor people, okay. So rich label has a great property that it has a realization set, first of all it is realizable, and we can find the correct corresponding realization set, whatever, let's call it S rich in polytime. But what can you tell about poor labels? What is the property of poor labels? What is the definition of poor? Huh? They are not much. Number of vertices that has been assigned poor label is bounded by how much? No. Read the definition. There are k labels and a label is poor if at most k guys are strictly less than k guys are assigned. So basically this is k minus 1 times k. So roughly like k square. So number of vertices that has been assigned a poor label is bounded by k square by definition. There is no epsilon here. Where is it? Read the definition. What?
If R is strictly greater than 1 minus
It does not matter whatever maybe the R is, whatever maybe. R is small, big, non-small, non-big, it does not matter. All I am trying to tell you, this is fine. Okay. Now what? Fine. So if this is a great idea, then we are very happy if the following happens. So what is the natural strategy? For all the rich labels, I find a witness set or realizable set, and suppose that this is the set X which I am trying to create. So I put S rich inside and put all vertices that have been assigned poor label. Right? Whatever may be. Right? Now all the independent set which is completely contained inside the rich label, we are very happy because we have. Right? We have kept, if a subset of independent set which is completely contained inside rich label, are we happy with that? Because in that X which I am creating, I have kept a witness set with respect to every realizable, every rich labels. So if you give me your S which is completely contained inside rich label, I am happy. Because this X contains, look at this as you were, it is exactly same as multicolor independent set. Similarly, if you gave me an independent set which is completely consists of all the poor labels, I am still happy because I have kept all the poor vertices. A label is poor, then all the vertices which have been marked with, let's call them poor vertices. I have kept all of them. So in particular, I can realize this set with epsilon equal to 0. But what happens, for example, if I have an independent set which consists of something from here, something from here, then I don't know. For example, I can have a set S which contains exactly half the vertices which are rich and half the vertices which are poor. I don't know what to do. What? But now I have an independent set which contains some poor vertices and some rich vertices. What?
There is no relation between the size of S and S prime.
What? No, there is no relation.
So even if I am given a set S which contains half of the rich vertices and half of the poor vertices.
But how do you know that there is a set which is independent? I just cannot take any set from here and any set, put them together, right? What is the property of S prime? There is another property of S prime, right? How? Look, yes, you are right, completely right. Look at this independent set. Okay, fine. Look at all the vertices in this independent set which have been assigned rich label. Take those vertices and this poor. But if I put them together, how am I guaranteed that that forms an independent set in my graph induced on X? How can we be so sure about it? We don't know. And that's where the problem lies. How do we handle these kind of structures, right? So we have a very nice strategy, right? Okay, so this will form a core of our algorithm. This idea will form core of our algorithm. But this is not good enough, right? Why it is not good enough? Because I take this set of vertices and I take this set of vertices, they are not good. Okay. Okay.
Using R is always realizable in H.
Yes.
But what stops from the following scenario? Look at the rich labels and look at this label. Look at the graph induced on the rich labels, and suppose it's a complete pattern graph.
It cannot. I'll give you a proof. Think about it. There are conditions.
Interval graph stops it from.
Yes. You just cannot draw any graph, right? This is why you have to restrict yourself to an interval graph. Of course, this does not hold, right? This we all know. This cannot hold. If I just have to take rich, as you are completely right, just take 2. You cannot take. Take complete, as you are saying, complete bipartite graph. I cannot define this, right? So you have to use the fact that you are working on an interval graph. So if you have to think of a counterexample or something, think interval graph. Interval graph has lots of properties. So what should be our strategy should be, right? Now notice, let's just try to think about it, right? If this is a strategy which we are going to have, and that's where the counterintuitive idea plays into picture. If this is an idea we are going to have, then whatever happens, it's good to take all the poor guys. Okay, fine, because I'm keeping all the vertices. It's just the rich guys which are creating all the trouble, right? Because they may not be an independent set, because whichever, this set in itself is an independent set, this set in itself is an independent set, but I do not, together they may not be an independent set. So this is definitely complete bipartite graph here, because this is an independent set because you have given me, and I have chosen an independent set realizing this, so it's a complete bipartite graph. But what I would like to do, I'd like to extend this. So now let's try to think, so this is an independent set you gave me, where does it lie? Where does it lie? Okay. So now I'm going to use the property of interval graph, or I'm going to draw interval graph to you. Okay. So now I'm going to rub this set this side. I hope you have absorbed the definition. So how does an interval graph look like? Okay, so we'll prove this lemma. This is A I need to show, B I need to show, I will show them. But how does an interval graph look like? Okay, right? I'm playing with interval representation, and assume that the intervals are between some 0, a, like where this is 0 and the last guy's right endpoint is some A, right? You can always also assume that these are over integers because you can stretch them. So always assume that they are over integers. It does not matter because anyway there are some 2 endpoints. So whatever that endpoint is, this is. Now let's try to understand what does it mean. Okay, so you gave me my S, okay, and I have partially constructed X at this point of time. What does this X consist of? Okay, let's what am I calling it? Let's call it. Okay. Okay. So S consists of S rich, and we are at some stage H. It doesn't matter. We'll construct, right? S rich realizing all rich labels. There's no S. I said S rich realizing rich labels in H. Where is S? I'll tell you. This is an independent set you will give me, and this contains all poor vertices. So this is what I have constructed at this point of time. Suppose I am in the beginning. So this is G, for example. Okay. Now you gave me an S any independent set. So I divide it into S rich, disjoint union S poor. Now I look at where the S poor are. So let's suppose S poor are somewhere, just two of them for example. And suppose this is my S poor, okay. But then where are my S, where are my these guys? Let's, oh, this is the very bad notation. This is a very bad notation. I shouldn't be calling it, let's call it, doesn't matter. Let's call it W rich or W rich, okay. Okay. Now where are these rich people are? Let's try to understand where are these rich vertices are. If these are my positions of poor vertices, so then where are these vertices? Because S is an independent set, so it cannot be intersecting with these intervals, right? So it cannot end because it forms an independent set. So what is an independent set in an interval graph? It is set of intervals which do not pairwise do not overlap. That's by definition, because how do you give edges in interval graph? You have vertices corresponding to every intervals, and if the intervals intersect, you give an edges. So basically now my other set of vertices will be somewhere here, could be here, could be somewhere here, okay. Okay. So what we are going to do at this point of time, they said, fine. Suppose I knew this, then I am going to look into this part of the graph, going to look into this part of the graph, okay. So it's like I don't know, but I don't know which are these guys are, but I know certain amount of things, okay. So this is like, if this is my first endpoint, these are endpoints. So what I know is that I look at my interval graph and I mark all the poor intervals because I know those, right, and that forms pairwise intervals, pairwise. So for example, it will form, say, let's mark all this point. No, this is not there. And this. For every potential pairs, I don't know what these are, like this or like this or like this or like this. I look at the corresponding interval graph and I will try to do something. How many such pairs are there? How many such graphs can I construct? K to the power 4. Because there are k square vertices, there are 2k square endpoints, and I am saying for any pair of endpoints, because I don't know which one of them will go and which one of them will go. I cannot say, okay, let's look here, because there are many poor labels, right? For example, I could have a poor label. This is also poor label, right? This is also poor label. This is also poor label, right? But I am saying that when I zoom into poor labels corresponding to a particular set, I forget about this. This is not a poor label at this point of time, right? I forget about it. But this is there. So what I try to do, I do not know whether for this particular set, independent set, which I am trying to find a realizable set which realizes most of its label, should I consider this interval, should I consider this interval, or should I consider this? I have no idea. I just don't know. So what I try to do, like a completely dumb person, I try all possible potential graphs.
So these orange edges that you've drawn, these are the poor vertices of S and not all the poor vertices?
No. So currently, yes. So for now, let's assume all these are poor vertices of graph for now, okay. But when I zoom into poor vertices of S, I only get this and I get this, okay, which implies that if I do not look at this interval and I would only looked at this interval, then I will lose this independent set, because this and this intersects, right, which I cannot do, right, because this, for the solution which you have in your head, for the solution, because you are an adversary, I don't know what solution of independent set you are keeping, right. I mean, if I do not consider this interval, then this guy, it means, look, I have taken the poor labels at this level, whichever is in my independent set. It means all other poor labels are not precluding other rich labels to be picked into the independent set, and we have to store this information, right? Right? If I just look at here, then this independent set will be gone, right?
So guessing which poor vertices will come from a specified X.
No, that's too many.
Number of poor vertices are k square.
But your independent set could be containing root k vertices. So I cannot guess that. That's too many. I'm not guessing. This is the point, right? But I know the possible graphs any S could be looking into, right? So I take, this is why I say, look at, let's make it all possible. So what I do, so there are lots of this. So what I do, if I have lots of this, then basically what I do is that for every, let's mark all the endpoints of all the poor labels, mark all the endpoints and include 0 and include the last guy. Now for every pair, I create an induced graph. Every pair, I create an induced graph for every pair inside this, right? Now, how many such graphs, induced subgraph I will create? At most, as many tuples of pairs. But now notice, if you had an independent set in your head, so you mark those guys. So here is a line here for him, and here is a line for him. That pair is also considered as an induced subgraph. So I will go into look into that place. Now this, so now even though I have not guessed the solution, but in some sense I have guessed which induced subgraph I must be looking into. Right? So this is a trick which I try. Now what I am going to do, so my algorithm is completely recursive. It tries to do this trick, right? It will find in this induced subgraph, it will find all the rich labels, put it like all the rich labels realizable set, put it inside this. It will take all the poor labels, now poor here, right? Poor here, and put them inside. Again it will keep doing this, but I cannot let this go on forever, right? It's like a branching tree. With what is a branching tree? It's a, think of this way, this is a branching tree with what is the branching factor? Roughly k power 4. Because in each h, I am going to do the same trick here. And at the end, I will take the union of all this set of vertices, right? But this will be a branching algorithm which will be truncated at some level. Okay, I will say, oh, after this, just don't do it. And what is this? It is obvious, right? At any point of time, how many vertices are we adding here? We are adding into X basically k square vertices here. We are basically adding k square vertices, some k guys here which realizes this, and all the poor vertices. So like k square plus k, something like this. In fact, k minus 1 into k plus k. At best, this is the number of vertices you add at any step. What is the size of set X in which number of vertices you add at any node? Is exactly this much. All the poor vertices and a set which realizes this, all the rich labels. What is its size? If there are only k vertices, k labels, I can find a set which realizes all the rich label of size k. So this is like k square minus k. So this is exactly k square. So size bound of what is this? I am going to add. So if I write down recurrence for the size bound, so what is this? Whatever this is. So depending on the depth, okay, it is going to be now whatever d is. How many branches of child I am creating? K power 4, right? Right? Whatever this is, and at any time I am adding this. So whatever this, what is the size? So I am creating these many childs. From each I will get some number and this. So basically if you think about it, this is basically going to be how many children are here? Let's think of this most obvious thing. If the depth of this tree is d, the total number of nodes in this tree is k power 4d, right? How many? If the depth of this tree is d and each vertex branches into k power 4 ways, then the total number of nodes in this search tree is k power 4d, and how many vertices we are adding at each one? K square. So this is going to be k power 4d plus 2, whatever that means, it does not matter. Now I need to set d appropriately. What should be the d? If I knew what I am looking for, then what is d? Is this. But the magic is that that's enough. Okay? So this is the whole algorithm. You might be wondering, why does it work? Right? So how will the proof of correctness will work? Look, what are you doing? Okay, fine. So look at your any set. How will I say? I say look at your fixed set. How will the proof? Look at your set. Okay, S which you gave me, all the poor guys which you had, you picked up here, covered them, put that into your set, because those are already realized. You're like, okay, now look into this guy, this guy, this guy, right? Right? So already all the poor labels has been covered. All the poor labels has been covered. But what can happen? A rich label can become poor here. A rich label can become poor here, right? Okay. But imagine if it did not become a poor, but amazing thing happened, right? Amazing thing happened. Okay. So think of this. So suppose, so now I know that once I picked all the poor labels, I should just go into some branches, not all the branches, okay? Because I am keeping union of them, everybody, right? So now let's look at here, let's look at some particular branches, right? Now what happens? Rich labels gets distributed everywhere. Like the rich labels here, like in the, or the vertices of your independent set which were rich, some has gone here, some has gone here, and some has gone here. And for now, for a moment, assume for a minute that they remain rich here. Then what happens? If they remain rich here, then you would have found the realizable set here, right? And you just put them together and then you have an independent set, right? Because by definition in this branch, whatever selection you made before is independent to whatever you are going to select later. This is what we did here, right? Okay, fine. But what is an amazing thing is that, fine, it does not have to be all the rich labels, but even if, so look, so S poor you picked completely. Look at S rich. S rich got divided into say S1, S2, S3. Now suppose here, number of rich labels here, right? Number of rich labels here is like 1, even from S1 I'm able to cover, even if from S1 at least 1 minus epsilon fraction of S1 remains a rich label. For example, if 1 minus epsilon fraction of S1 remains a rich label here at this point of time, at any point of time, then I am already done. Why? Because then S poor plus 1 minus epsilon times, right, S1 plus 1 minus epsilon times S2 plus 1 minus epsilon times S3, right. So you take 1 minus epsilon common, S1 S plus S3 will be equal to S rich, S poor is whole thing. So you are able to cover really 1 minus epsilon fraction of this. Okay. So the problem is when, what happens? Okay. So let's think what is happening. So why our algorithm which is trying to construct did not step at the first step? Because the number of rich labels, for your solution, among them suppose there were some rich labels, number of people who went from rich to poor were too many, right? It was much more than epsilon fraction of them, because if it was at least 1 minus epsilon fraction of them, then just take it here, you don't need to go further down, I don't care about it. Because the only reason why you have to go further, because the number of rich labels is losing by epsilon, you are losing an epsilon fraction in every step, every branch you are losing, otherwise you will stop the moment. Suppose I have some set of rich labels at this point of time here, right? Suppose I have some set of rich labels here at this point of time. In the next iteration, many of them remains a rich label, like at least 1 minus epsilon fraction of them remains a rich label, then I am done, right? Then I don't. But if it remained, but what happened? At least epsilon fraction of them become poor. But that's great for us also anyway, because then you have picked up all those poor guys in your solution. So you keep going. So problem is, so what happens? So this is what, so you are losing epsilon fraction here, you are losing epsilon fraction here, but you are losing epsilon fraction of what? Epsilon fraction of remaining guys, right? So if you do the maths, if you go at that many level, what will be left of the rich people at the end when you stop, number of rich vertices which is left, right? Because you are losing epsilon times rich label every step. So suppose rich was k, say k. So in the next step, how many rich labels are left? At least you have lost epsilon times k or k rich labels. So only little are left. Next time you again left, what you left? Epsilon of that 1 minus epsilon k, you lost, right? So you keep doing this, you keep doing this, you keep doing this. So you can show that at the end of that, you know how many rich labels are left? At most epsilon k. So or epsilon times rich labels. At the end, the bottom, when I stop after that many steps, look at this path, right? Number of rich labels which is left at the bottom to be killed is epsilon times the rich label. And I said at this point of time, I sacrifice all of you, go to hell, right? So basically what happens, look at every step, if every depth you go, look at the rich label. The reason why it is going to the next step, because it loses certain fraction of its rich label to the poor people. And then it's great for us in that case, because then you pick up all of them. But the worst case is that you're losing little in the bottom, but you're still losing something. So if you do the maths, let's do the math. Look, I'm only giving you an overview. I am not giving you a single proof materialistically. I'm just giving you an intuition. Okay. So this is what. So like this is, let's try to do the maths, right? If happened, okay, we'll prove it formally next time. Okay. Everything will prove it formally next time. It's not that after this you cannot construct a proof from here, but let's suppose, okay. So why did we not? So suppose here is a path, okay. Here is a path of length d, okay, and I started with k labels which are rich, okay, k labels which are rich or whatever that means, some. I reached here, why? Because number of rich labels here is less than equal to 1 minus epsilon times k, okay. So how many rich labels are here? What? It doesn't matter, right? We are just doing a very rough computation, strictly less. Okay, now it is 1 minus epsilon of this, right? So these are, I'm losing. So when I come here, how many I have lost? D times k. Okay, so these many labels I have lost. No, so this is the left, this is the left. So these many labels, rich labels are left after d step. At most this many, agreed? Right? So what is this number? Let's try to understand this. So this is at most rich labels. The total number of rich labels which has become poor is 1 minus epsilon to the power, let's do this computation for you so that you see the maths at least happening. Not that this is very important. Okay. Look, I could give you a proof completely by proving formally, but it doesn't help that much. So let's do this computation. Okay, this is a very important thing which happens. Okay, so what are we trying to show? We are trying to show, so how many rich labels are left at the end? This much, and I'm claiming to you 1 minus epsilon to the power dk is actually less than equal to epsilon times k, or whatever the rich label you started with. So let's call it k star is the total number of rich labels, so that let's not confuse, right? I have to show that this is this, right? Because you have got all the labels which have been poor, right? So in this whole process, the moment someone became poor, you were very happy because you got all those guys. The only reason you couldn't get these rich guys because you truncated your algorithm in the middle. I said, okay, this is enough, this step, I stop. So I lost all those rich labels at that point of time, which remained rich from top to bottom. That's the only time, right? So, but how many of them are left is this. I want to show that this is this. Huh?
Shouldn't it be 1, like if it is at most 1 minus epsilon k in the first step, shouldn't it be 1 minus 2 epsilon k in the second step?
No, because it is 1 minus epsilon fraction of what is remaining.
So it is basically at every step it is k minus k epsilon. 1 minus epsilon k is k minus epsilon k.
Yes.
So after the first step, your k becomes 1 minus epsilon times k.
Yes. So I took 1 minus epsilon of that. That is why I have square, right? It's the same thing. You just try. Why you want to write k minus this and kill yourself, right? So this was this is left, this is, that's so, otherwise you will, maths will go wrong, okay? So k star goes cancel, right? All I have to show, I mean, is 1 minus epsilon, what was that? Huh?
1 by epsilon into log of.
So is this correct? This should be correct. Like, of course there is some ceiling, this is some integer, so you have to put some ceilings or floor, it doesn't matter. Okay, so take, I mean, how do I do this? I really don't know, but okay, look, wait. So this I can write. So what is this? 1 minus 1 by n to the power n is what? Minus 1. E, what is this? What is this? Right? E. So this I can write 1 minus 1 by epsilon, right? By 1 by epsilon log 1 over epsilon. Agreed? Is this correct? Right? So this is roughly e power log 1 over epsilon. So it is e power minus log 1 over epsilon. Yeah. Okay. So what is this? Yeah. So this is nothing but, if I go get 1, it becomes e power log epsilon, which is basically epsilon. Of course you have to choose constants. So this is fine, right? If you have ever done maximum covering maximum number of elements with k sets, covering maximum number of elements with k sets and get 1 by e approximation algorithm for that, this is exactly what this math says. I did not prove anything formally, but that's an intuition that Oh, this is great because I can truncate in the middle, right? Of course, I will make everything formal, but there are only 7 minutes, so I cannot do that. Okay. So in the next lecture, I'll prove this everything formally. I have to prove how do you make such transition, how do you find such an object. But once I have told you, the algorithm is just this is the algorithm. You do rich label, rich, poor, and what is the proof of correctness? Oh, you give me your set S. Okay, I follow the path in this branching tree. Right? I follow this path in the branching tree and I'm happy. Right? So whatever the set, whatever the vertices of your set you are able to pick up. In fact, what does this gives us? In fact, if you notice, except when you stop in the middle, because the number of rich people remained lots of rich people, that is a time when you would have computed any set which would have realized that, right? And that is the time you are going away from the set which you have given me. Otherwise, if I reach in the bottom, then I am actually returning you a set which is completely contained inside your set, and it is of this. But only time when I do not return, because here what I said, here if the what I will do algorithm will be, my algorithm will be, oh, if the number of rich labels is because if the number of rich labels, whatever I do is that if the number of rich labels of my particular independent set is more than 1 minus epsilon times whatever I started with at this point of time, then I have already a set which realizes all the rich labels. I pick that subset from that and I return that, and that's it. I don't go below, right? So at that point of time, I may not have returned. So I have given you a different set which realizes almost all the labels of your set, and that's the whole thing. Okay, so where did we use interval thing? Okay, there are several places we will use interval. First, to find this. Second, because this forms an interval, I have a k power 4 canonical ways of branching, right, which translates to choosing all possible subsets from the poor labels, right. I have got polynomially many instances which is able to cover every potential cases of your taking the subsets, because I do not know. If I would not have this linear order, I would not know which induced subgraph to take if I started with an arbitrary graph, right. So basically, as you notice, what did you say? Basically what you are doing in the beginning is that you guess something, and based on this each possible subsets you are trying to find in the remaining graph. If I give you an arbitrary graph, right, I do not have a canonical induced subgraphs which are polynomially many, and it covers all the cases for selecting a subset of independent set from the poor labels.
Can we do similar kind of things assuming that lemma for say bounded tree with graphs?
Of course you can do bounded tree with graph. What's the big deal?
There's nothing special about the bar.
No, no, sorry, bounded tree with graph, I don't know.
I mean, assume you have such a lemma.
For then also I don't know how to do it.
This thing.
Now then I don't know how to do it. How will I cover this? How will I cover this?
So it's like every bag is a separator. So basically you are partitioning the problem into independent problems, right?
No, I don't know. From the bag you might be picking lots of people.
I'll take all.
Yeah, that probably might just work. Yeah, that could work for graphs of bounded tree with.
No, but you're correct. If I'm picking everything from the bag, then at every point I'll pick everything from the bag and I'll end up picking everything.
No. So look, so what you did, suppose you marked all the bags which contains the poor labels. Okay, so you have to apply a different strategy. What I will do is following. I have but a vertex can appear several times. Okay, a vertex can appear several times. So for every vertex, what I do, I look at my tree decomposition and I have a rooted tree decomposition. I mark the topmost node. Okay, like after this I lose. Like this is a bag after which we forget this. Okay, so let's mark all those guys. So how many such nodes I will mark? If I have a k square poor labels, then I will mark k square such objects. Okay. Now what I do is that I do a transitive closure of this, not transit. What is that? What I LCA closure of this. So I will mark another order k square. Now I delete everything so that everything just falls apart. And how many such connected components I will get? Whatever it is, I just do it on all of them. Right? But then in my set, I have only picked up this much, which is, I mean, I'm like okay, it will require proving in a certain way, but it can be proved. It might work for graphs of bounded tree width. Okay, and maybe on graphs of bounded tree width one can find such a realizable set, because it is nothing but some kind of degeneracy argument. Okay, so with that in mind, okay, this is a combinatorial object. Okay, one can try to find different set of parameters to optimize for different graph, which has nothing to do with algorithm. Right? Look, my motivation is an algorithm, but one can have a motivation which is not completely algorithmic. Okay, so what we will do on Friday, if we do have a class, which we may not have a class depending on my schedule for some other things, like I have a deadline. So, but if we do have a class, what we are going to see, at least in that class, is a complete proof of this, like really formally proving everything. What I have done today is give you a completely intuitive picture of why this works if you start from this, and it took some 2.5 years to get to all this. I mean, in retrospect, everything looks nice, but or simple, but to be able to find the right definition, right object, it takes years to build it.